AP Statistics students, there's one more part of Chapter 6 to review, and that's at the very end, Section 6.3, binomial probability. Binomial probability addresses a special kind of random variable. A binomial setting and a binomial random variable. A binomial setting occurs when you have a fixed number of trials in a random process. There are only two outcomes referred to as success and failure. From trial to trial, they are independent, and the probability of success is the same for every trial. Example, randomly choose 10 people and check to see if eye color is blue or not blue. So you see, we're randomly selecting 10 people. There are only two outcomes, blue and not blue. Isn't it true that the trials be independent from person to person? Whether this person has blue eyes doesn't affect whether this person has blue eyes, as long as they're not family members. One outcome does not affect the other. And isn't the probability of getting blue eyes every time you check a person the same amount? Okay, whatever that is. Now, a non-example, randomly choose 10 people and see if their eye color is blue, brown, green, etc. Well, you see blue, brown, green, that's more than two outcomes. So then that's not a binomial setting. All right. Now, the binomial probability formula. When we taught this in Chapter 6, we taught the binomial probability formula when you have to make a calculation by hand, but we also taught that the calculator can just calculate binomial probabilities for you. You've got to know the binomial probability formula because sometimes they structure a multiple choice question with the formula instead of the actual percentage answer. So here's the binomial probability formula. I'm hoping you remember it. Let x equal a binomial random variable going through n trials. The probability of having k successes is given by the probability that x equals k is equal to nck. That's the combinations formula. It tells us how many different ways that k successes can occur, multiplied by the probability of success to the k power, multiplied by the probability of failure to the n minus k power. So suppose that you're given this example. It is known that 11% of a population is left-handed. If you randomly select 20 people from this population, what is the probability that exactly 5 of them are left-handed? So in this problem, the probability of being left-handed is 0.11, n is 20, and k is 5. So if we wanted to say what is the probability that x equals 5, having defined let x equal the number of left-handers. So when you say what is the probability that x equals 5, you're saying what is the probability the number of left-handers is 5. Well, that's equal to 20c5 times the probability of success, which is being left-handed, to the k power, times the probability of failure, meaning 1 minus 11%. So there's an 89% chance of being a non-left-hander, to the 20 minus 5 power. Now, you might remember I told you sometimes instead of putting 20c5, what they'll do is they use this other notation where they put 20 stacked on 5 in parentheses. So you could see this as the answer in a multiple choice setting. What is the probability that less than 3 of them are left-handed? Well, wouldn't that be equal to the probability that x is equal to 0 plus the probability that x is equal to 1 plus the probability that x is equal to 2. So then you need to be able to find the multiple choice answer that looks like this. 20c0 times 0.11 to the 0 times 0.89 to the 20th plus 20c1 times 0.11 to the first, 0.89 to the 19th, plus 20c2, 0.11 to the second, 0.89 to the 18th. Again, they don't go here a lot, but just in case they structure a multiple choice question where instead of giving you the percentage answer, they give it in the structure of the formula being used. You've got to know that formula. However, oh yeah, one more slide before I say however. We also learned how to calculate the expected value, also known as the mean, and the standard deviation of a binomial random variable. The expected value of a binomial random variable is e of x equals np, where n equals the number of trials and p equals the probability of success. So, for example, on our left-handed problem, the expected value of x, where x equals the number of left-handers in 20 people randomly selected, is equal to n times the probability of being left-handed. And so if I grab a calculator, grabbing a calculator, 20 times 0.11 is 2.2. So in other words, every time I randomly select 20 people out of this population, I would only expect about two left-handers to be found. Okay, so if I only expect about 2 left-handers to be found in any random selection of 20, doesn't that say the probability that x equals 5 would probably be a low chance? In other words, if I punch this into the calculator, it would probably be a small number. Okay, now the standard deviation of a binomial random variable is the standard deviation of x is equal to the square root of n times p times 1 minus p. So for the left-hander problem, that would be 20 times 0.11 times 0.89. So let's see, 20 times 0.11 times 0.89, and the square root of that is 1.4-ish. Okay, all right, now let's think about this in terms of a distribution. We expect about 2 people to be left-handed. If I randomly select 20 people, I could find 0 lefties, 1 lefty, 2, 3, 4, 5, all the way out through 20 lefties. Well, since we would expect about 2 out of 20 to be left-handed, that would be the most probable outcome. And anything close to 2 people would probably also be a fairly good chance. But when you get out to the probability of 5 people or 6 people or 7 people or 20 people, of the 20 people being left-handed, we would see that this distribution would be skewed to the right in all possibilities of how many left-handed people we'd find in a group of 20 people. Now, we also learned about the binom PDF and binom CDF commands. In a multiple choice question setting, you want to be able to get answers quickly, of course, and so sometimes, unlike the first example, they give you the answer choices in terms of percentages. So remember, the binom PDF command calculates the probability that there will be exactly k successes in n trials. Okay, so how to use the binom PDF command? So what is the probability of finding 5 left-handers in that group of 20? Well, that would be binom PDF. And then the binom PDF command, if you pull it up on a graphing calculator, takes 3 numbers. It wants the number of trials. So if we were still choosing 20 people, comma, the probability of success. Well, for us, that was 0.11, 11% of the population is left-handed, comma, the number of successes. So those are the 3 numbers, and then the calculator will just spit out the answer. Again, this answer would probably be lowish. The binom CDF command calculates the probability that there will be less than or equal to k successes in n trials. So what is the probability of getting less than or equal to 5 left-handers? Well, that's binom CDF 20.11 and 5. See, when you change it to CDF, what it's doing is it's finding the probability of getting 0 lefties plus the probability of getting 1 lefty all the way out to the probability of getting 5 lefties. So that's a nice command. In order to calculate the probability that x is greater than or equal to k successes, you use the complement rule. If I wanted to find the probability that x is greater than or equal to 5 left-handers, that would be equal to 1 minus binom CDF 20.11 and 4, because the binom CDF command 2114 adds up 0 through 4, and then if you subtract that from 100%, you have 5 through 20. All right, so hopefully this video helps you remember binomial probability a little bit.